right, so hopefully a name from the past that brings upon great memories is Avogadro. Came up with this little number of 6.02 times 10 to the 23rd, number of anything in a mole. Mole being our most important unit within chemistry. Again, if you don't know what to do in a calculation, convert to moles. Hopefully that's all ringing the bell to you. Here is what he stated. Equal volumes of gas at the same temperature and pressure contain the same number of molecules. This statement is able to be made due to what we read about last class. Because in essence, what he's saying here is it doesn't matter what the gas is. Any gas at the exact same temperature and pressure will have the same number of molecules in a certain volume. Doesn't matter of the size of the molecules. Again, last class, with the group doing the reading guide, I brought up the fact that Kirsten's a lot smaller than Joe. Kirsten's so small that when I ask her height, she gives me to the half an inch. That's an indication that you're short, Kirsten, because my wife does that as well. I hope you're okay with that. Joe, what's your height? 6'2". He did not say 6'2 and a half or anything silly like that, because when you're tall, you just round off to a number. We can fit 24 Kirsten Bennett's in this room. We can fit 24 Joes in this room. It doesn't matter. We have 24 seats, regardless of the size. So that's what Avogadro's law is basically saying. Because gas molecules are so tiny compared to the volume that they're zipping around in all day long, it's an equal amount either way. Again, our school has a certain capacity that we can have. It's not a capacity based upon those that are under 100 pounds and those who are over 200 pounds, because we have probably both in this building. It is just a number of bodies, regardless of the size. Because remember, gas is really tiny compared to what space they occupy. So that's what I'm saying with this second point here, is this allows us to use this for any gas under ideal settings. Hence it's called the ideal gas law that we're moving into. Now the ideal gas law starts to fail us if we are no longer in ideal settings. That would mean if pressure was really high. Because when pressure is high, molecules are closer together, more likely to interact with one another. Cause them to, their behavior be offset by the other molecule. When temperature is really low, they're moving slow, more likely for them to be reacting and interacting with each other. So the ideal gas law does have to be at not ridiculously high, not really low temperatures in order for this to hold true. But if this were the case, at standard temperature and pressure, for example, 1 mole of any gas would be 22.4 liters. I have that in a box right next to the thermometers that you used for the can crushing to give you kind of visualization of what is 1 mole of a gas. In Chem 1, we are just now introducing mole conversions for the first time. So I show them a mole of solid carbon. They don't know yet that all we have to do is measure out 12 grams because I've only gone over Avogadro's number. I can show them a mole of aluminum. Now, solids will take up a different amount of space because the particles are already packed in tight. Gases are so loosely packed, that volume works for all of them. If you don't remember that number, it's okay because you can calculate it at any point using the ideal gas law. We're going to show you that in a second. However, sometimes knowing that number at STP allows you not to have to do a calculation and get through a problem really quick. So that's kind of why I bring that up. As for the ideal gas law, it's PV equals nRT. Hibner. This equation is given to you on the AP exam. Usually, equations that are given to you in the AP exam are ones that they have to give you a little bit more information for. So it's common that they'll mention, hey, P is for pressure. Although, they probably will not say in the equation sheet that pressure has to be in atmospheres. In order to use the ideal gas law, pressure has to be in atmospheres. V for volume. Volume has to be in liters. So once again, we got done doing the combined gas law. Those units don't matter as long as they agree with each other start to finish. This, however, it does make a difference. Lowercase n in chemistry stands for the number of moles. It is an abbreviation that's used fairly often for other things as well. We will use it for something else starting next class when we talk about partial pressure. T is the temperature, has to be in Kelvin. And last but not least, R is a constant. Somebody at some point figured out, hey, if I'm going to do a whole bunch of circle math, this 3.14 number works out really slick for it. Pi is a constant. R is a constant. Somebody figured out, hey, in order to do these calculations, this number helps me make it work. Ideal gas law constant of 0.0821 liters atmospheres per mole Kelvin. The reason why the ideal gas law is unit specific is because the constant is. That constant doesn't work if you are now in millimeters of mercury. Look at the units of the constant. It tells you what the units that you have to use for everything else. That R value is given to you. However, there are more than one R values dealing with gases, depending upon what unit you use. So there's an R value dealing with work that's going to have joules in the unit instead. And I believe there's a third R value that I don't even show in class because we never really use it. So when you get your equation sheet for your unit test for me or for the AP exam, you got to be able to see which R value am I using based upon the problem. And with this type of problem here, when you see the units for the R value, it tells you volume has to be in liters, pressure has to be in atmospheres. I need moles. I need Kelvin for my temperature. Okay? If I show you one sample problem here, I could ask something as simple as 1 mole of methane occupies 20 liters at 1 atmosphere. What is the temperature of the gas? My original equation is this. You have two options. You could plug in 1 mole, plug that in for N. 20.0 liters, plug that in for V. 1.00 atmospheres, plug that in for P. R is a known value, that's the constant, so you just plug that in, you can solve for T. Otherwise, you could isolate the variable. So I just wanted to remind you of how you could do that. By dividing both sides by NR, you could have T equaling PV over NR. And then you could plug in at that point. Whichever way you're more comfortable with, you do it that way. Either way, I get 244 Kelvin as my answer. One thing I would mention about this particular problem is when in word form it gives you 1 mole, that doesn't help you out when it comes to sig dates at all. So we would actually give them to your numerical value instead. Last thing to bring up before we start doing practice problems with this, and then that's basically our day, is you've now seen 2 different gas laws. They are used in 2 different ways. The number one issue with AP students when they take a test is they don't know what to use and when. Because WebAssign just says, hey, this is the Boyle's Law of practice problems. It's very straightforward. In AP Chemistry, though, it's just a problem that gives you numbers and you have to figure out something with it. So here's what I can say about it. Combined gas law is kind of a before and after scenario. Before the can crushed, after the can crushed. And you're going to see a lot of variables given to you in that one. How do I identify the ideal gas law then? To me, it's the N value. It's the number of moles. Because the gas laws that you've seen in the past 2 days prior to this give you no mention of the amount of gas, the N value. And by the way, it might not just be moles that's given to you, it could be grams that's given to you. If you see grams of gas given to you, that should be a dead giveaway that you have to use PV equals nRT, because we know how to go from grams to moles using our periodic table.
The equation sheet will give us like that number.
It does give you the 0.0821, yep. And to me, not only is that important, but it gives you the unit afterwards. Honestly, when I solve these problems and I plug in, and I bet when you look at my answer key, it's going to hold true. I don't write down the unit for R when I solve this because it's a long-winded unit. but the unit does help you identify, hey, my temperature has to be in Kelvin, my volume has to be, and that's the other thing, where combined gas law, it doesn't matter. Combined gas law, as long as the ones and the twos on the two sides of that equation are the same unit, it's fine. Ideal gas law is unit specific because of that R value alone. Now, some people then automatically just always convert to liters and to Kelvin and to atmospheres whenever they do any gas law problem from now on. And if you want to do that, it's fine by me. But even like the can crushing we did on the board, you don't have to. We were in milliliters, we were in millimeters of mercury. It's up to you guys to keep track of what to use and when, and then how to use it. Because the two equations I've shown you today, I don't think are overly difficult. It's just that students get things mixed up at times. Okay?